All right, welcome to Lecture 12, Engineering 270. So our subject today is floating point numbers. If you think about it, everything we've done in 250 and in 270 so far has dealt with integers. Weighted positional notation, so an 8-bit integer, we have 8 digits. Each digit is a 0 or 1, and each place corresponds to an increasing power of 2. And if we have a 1 somewhere, it represents 1 times that power of 2, and we add all those things together, and it gives us an integer typically from 0 to 255 for 8 bits. We introduced 2's complement notation in 250 to represent negative numbers, in which case this leading bit, being a 1, indicates the number is negative, and we had an algorithm for converting between positive and negative. But it's still an integer. And in scientific computation, in most other things we do with computers, we really want to deal with things other than just integers. We want to be able to write a number like 1.5, right? You saw this when you were doing pulse width modulation. Sometimes you wanted a period register of exactly 4.5, right? And we could have a 4 or a 5, but there's no way that we could represent a number in between two integers. And so the challenge is, how can we represent numbers like this, or the number pi, or any general number that we want, using this what seems inherently integer notation. And so remember something that I've said before in 250, if you had me in 250, there's no inherently right or wrong way to represent things using binary codes. There's ways that we agree upon, but there's nothing inherently about this which says this must be the integer number 3, right? If we think of it as weighted positional notation, sure, that's a 3. There's nothing about this which says this must be the number 0. It looks like a 0 because it's got all these zeros, but it's a fairly arbitrary assignment between bit patterns and things that they represent, whether those things are integers or real numbers or characters of the alphabet or anything else. So we're going to talk about a different kind of coding, a way to code numbers that allows us to represent real numbers, okay, things that aren't just integers. And this is a standard called IEEE 754. Standards are important because I might represent floating point numbers, right, real numbers like this. I might use one type of representation, and you might use a different type of representation. And if we live in our own worlds and we never meet, that's fine. But if I've got some data and you want to process it, and I send you my data, and it's coded with a different representation from how you code things, you're not going to be able to use it, or you're going to have to come up with a conversion algorithm, right? So there's a standard that we use now to store these real numbers, these floating point numbers, and it's called IEEE 754. So here's the inherent challenge, right? We have two things we want to be able to do. Number one, we want to be able to represent a large range of numbers. If you think about it, if we're doing astronomy, we want to be able to represent numbers representing huge distances, right? So, 10 to the 30th, right, should be a reasonable thing to represent. But if we're doing very, very small work, if we're doing something in biology, or if we're looking at quantum systems, we might want to be able to represent very small quantities as well. So this is a huge range, right? Many orders of magnitude difference. And we want to be able to represent numbers with both of these. The other thing is we want some sort of precision. A lot of things that we deal with in science have an inherently small magnitude, but lots of things after the decimal point, for example, the number pi or the number e. And so we want to be able to capture things to the right of the decimal point, but also have very large and very small numbers, right? And so there's some tension between this, and so this is one reason that people had different ways of coding these floating point numbers. So let's look at IEEE 754 and let's see what the current standard is for storing numbers. And single precision is 32 bits. There's a 64-bit version that's so-called double precision, and we'll touch on that briefly. But let's mostly work with 32 bits, because if we can understand how to store things in 32-bit notation, or how to take a 32-bit floating point and interpret it correctly, then we can do the same thing with 64 or most other representations. So what do we do with these 32 bits? Well, there's going to be a fractional part, and the fraction is stored in the lower 23 bits. So we'll just call that fraction, and it goes from bit position 0 to 22. From 23 to 30, that's an 8-bit exponent. And this last bit, 31, that's a sign bit. Okay, so if you have a number in this form, in general, here's what it represents. -1 to the s times 1 plus the fraction times 2 raised to the exponent minus 127. Okay, what the heck does all this mean? Let's look at the sign bit first. Basically, if s is a 0, minus 1 to the 0 is 1. This is just positive 1. But if s is 1, minus 1 to the 1 is negative 1, so this is negative 1. So this is just either having no effect on this if s is 0, or it's negating this if s is 1. So we can think of this as s equals 0, your number is greater than or equal to 0, s equals 1, your number is less than 1. Sorry, less than 0. Right, so it's controlling the sign, whether the number is positive or negative. And our fraction is basically going to, our number is basically going to be some fractional part multiplied by a power of 2. Okay. The power of 2 is 2 raised to whatever this 8-bit exponent is minus 127. So it's a little different from just a plain old integer being coded in binary. We actually take the integer we want to code and we add 127 to it. Why do we do that? Well, there's technical reasons why this makes some of the processing easier, but it's kind of like just another way to represent negative numbers. So if our exponent was 0, 126, 127, 128, 255, well, over here, this piece would be 2 to the minus 127. This would be 2 to the 126 minus 127 is negative 1. This would be 2 to the 0, 2 to the 1, all the way up to 2 to the 128. So this is what we call an excess notation. We basically add this bias. Okay, so here's terminology. Bias equals 127. That's the amount that we're adding to the actual exponent that we want to get the exponent that we store. We'll play around with some examples that'll clarify this. It's kind of confusing to try to describe, but it's pretty easy once you see it to understand what's going on. Basically, we store an 8-bit number in here, subtract 127 from that number, that's the power of 2 that we're going to multiply by. And when we multiply, well, basically this fraction, we think of a decimal point sitting right here. Well, we always assume there's a 1 to the left of the decimal point. So if we stored all zeros in here, it's not going to be something multiplied by 0, it's going to be something multiplied by 1 point, bunch of zeros. And this is very much like something you're already familiar with, which is scientific notation. So if you want to represent the number 1436.5 in scientific notation, it's 1.4365 times 10 to the, and you go 1, 2, 3 places to the left, right? And in scientific notation, we move this decimal point so that there's always one digit to the left of it. But in binary scientific notation, our digits are either 0 or 1. and if this is not a 0, it's got to be a 1, so we don't bother storing it. So we only store this part. This is the fraction. And then the exponent is basically this 3, except we have this weird business of adding 127 to it, so we'd actually store a 130 in this case. And if we want negative, we put a minus sign in front. If we want positive, we put a positive sign in front. That's what the sign bit is. It's a 1 for negative, a 0 for positive. So this is really an extension of scientific notation to the realm of binary numbers. So it's something that we're kind of familiar with, but because we're working with binary, it's going to feel a little different. We're going to take advantage of things like the fact that if the thing to the left of the decimal point is not a 0, it's got to be a 1, so we're not going to represent it. Okay, so next video, let's get into some examples and see how this actually works.